Which of the following triangles are similar to triangle ABC? So this is triangle ABC, ABC. Before we even look at these options, let's remind ourselves of what it means for two triangles to be similar. There's multiple ways of thinking about it. The classical definition of similar triangles is that all of the corresponding angles are equivalent. So for example, if these two are similar triangles, then if this angle corresponds to that one, then these two angles are going to be the same. If this angle corresponds to this one, then these two angles are going to be the same. And if this angle corresponds to this one, then these two angles are going to be the same, and these are similar. And the reason why similarity is useful because that tells you that the ratio between corresponding sides are going to be the same. So for example, if this side has length 2 and this side has length 1, then the ratio of this side to this side is 2 to 1. The corresponding sides here are this side and this side, so they would also have to have a 2 to 1 ratio. So for example, this could be 4 and this could be 2. 2 to 1 ratio. 4 over 2 is the same thing as 2 over 1. Or it could be 7 to 3.5. Or it could be 10 to 5. It would always have a 2 to 1 ratio if this had a 2 to 1 ratio and if these are similar triangles. Now, in the context of a line and slope, I'll think about another one, another way of thinking about similarity. If you have two right triangles, so let's say this is one right triangle right over here. So if you have one right triangle right over there and you have another right triangle, just like that, if you have two right triangles, and the ratio of the two sides on either side of the right angle correspond to each other. So if the ratio of this magenta side to this green side is the same in this triangle as it is in this triangle, then we are similar. So for example, if these are two right triangles, and if this is let's say this side is length 6, and this side is length 9, and this side is length 2, and this side is length 3. These are going to be similar triangles. You have an angle right over here, and the ratio 6 over 2 is the same thing as 3 over 1. Ratio of 9 over 3 is the same thing as 3 to 1. These are similar. Similar. Now, why am I telling you that in the context of this right over here? Well, when we have a line and you connect any 2 points on the line, let's say point C to point A, the ratio of your change in y over your change in x is always going to be constant. And when you have a right triangle, or when you have a triangle constructed this way, where you have your change in x is going perfectly horizontal and your change in y is going perfectly vertical, it's going to be a right triangle. And so any right triangle you construct between 2 points on the line this way, they're going to be similar because your ratio between your change in y, notice if you go from point C to point A, you can see point C is at 3, point A is at 9. This is literally your change in y. Going from 3 to 9, you increased by 6. Your change in y is equal to 6 right over here. And in the horizontal direction, this base of this triangle right over here, this is your change in x. C is at your x value is at 1. A, your x value is 3. So your change in x is equal to 2. And any right triangle you construct this way between any 2 points on the line, this ratio, your change in y over your change in x, which in this case is 6 over 2, is going to be constant. And since that ratio is going to be constant, it's a right triangle, any two triangles constructed in this way with the line between 2 points on the line, they are going to be similar. Now, let's look at our options. So triangle ADG. So triangle AADG. Well, once again, the hypotenuse, just like triangle ABC, the hypotenuse is still our line. We are essentially thinking about the base of the triangle is the change in x. The change in x between going from D, between our x value for D and our x value for A. And this height right over here, or this side right over here, this is our change in y, going from y equals -3 to y equals 9. So this is our change in y. We know that your change in y over your change in x is going to be constant for a line. This is a right triangle. So these two triangles are definitely going to be similar. And if you want to break out a little bit of your geometry, it's not hard to prove that the corresponding angles are equivalent using a little bit of your parallel lines and transversals of parallel lines knowledge. Now let's look at triangle BEF. BEF. Well, this is a right triangle, but its hypotenuse does not sit on, so triangle BEF. So this triangle is a right triangle, but its hypotenuse does not sit on the line. Now, it could be similar, but you could even see that this line right here has a different inclination and it has a different slope. So that's a pretty good sign that these are not going to be similar triangles. And if you really wanted to verify it, you can look at the ratio of your change in y over your change in x. And in fact, let's just do that for fun, just to prove to ourselves that it's not similar. So this, let's see, to go from f to b, you're going from -6 to 3, 3 minus -6. You're changing, I'll just say this length right over here, BF, is equal to 9. I'm not going to say change in y over change in x because we're not going between 2 points on the line. I'm just going to look at the length of this line. The length of this line is 9. The length of this line right over here, let's see, we're going from -1 to 3, is 4. So the ratio of 9 to 4 is definitely not the same as the ratio of 6 to 2 or 3 to 1. So we can rule BEF out. Now let's look at EFG. EFG, well, once again, this isn't sitting on the line. That doesn't necessarily mean it's not similar, but you can even see the inclination of its hypotenuse is very different than the line right over here. And you see the ratio of these sides. You have a side length 3, side length 4. The ratio of 3 to 4 is definitely not 6 to 2. If this was somehow oriented different, the ratio of 4 to 3 is also not the ratio of 6 to 2 or the ratio of, or I guess this is the 6 to 2, the 6 to 2 or the 3 to 1. So we can rule this one out as well. And then finally, triangle BDG. So BDG. Well, once again, you're tired of me saying this. Triangle BDG, its hypotenuse does not sit on the line. Its hypotenuse has a very different inclination or a very different slope than the line itself. So this is not going to be a similar triangle. And you can often eyeball it. A similar triangle will look the same. It'll have the same proportions. They don't necessarily have to have different sides or different sizes, but they can have different sizes. One is a scaled up version of the other. And you can see here, this triangle right over here looks very different than triangle ABC. And you can even verify that the ratio of this side right over here to this side is very different than 3 to 1. So we can rule this one out as well. So let's actually input that and make sure that we actually got the right answer. So let me input it right there, and we got the right answer.